Alright, so I want to go over the quiz that we took yesterday. So first thing I want to say is almost everybody got numbers 1, 7, and 8 right, which is absolutely phenomenal to have 100% of people get those correct. 3 people missed number 3, like 3 people missed number 5. So that's not too bad. The ones I really want to talk about were 2, 4, 6, and 9. Those are the ones that a lot of people really struggled with. 2 and 9 were the math ones that people struggled with. 4, well, we'll go over 2 first. So number 2, if we look at number 2 on our paper, it asks us to determine the volume of SO2 at standard temperature and pressure formed from the reaction of blah blah blah, and it gives you the molar mass, and it gives you other temperature, pressure, and it gives you the reaction equation. Okay, so there's a lot of information in that problem, and we kind of have to figure out what to do with all of it. Okay, so the first thing to notice is that they give us 96.7 grams of FeS2, and they give us 55 liters of O2 gas. Okay, what that tells us right away, if we put those over top of, is what we have 2 reactants, and we're looking for the volume of SO2, which is a product. So whenever we have 2 reactants and we're looking for some information about our product, we know that this is a limiting reactant problem. So very first thing we have to do is figure out which one of these 2 is our limiting reactant. So let's start with grams, because we have already been given the molar mass. So we know whenever we have grams of a reactant and we have a chemical equation, the first thing we want to do is convert to moles. Whenever we have a chemical equation, we pretty much want to convert to moles. Okay, then we can use our mole ratios. So we have 96.7 grams. So let's do that first. So we're given 96.7 grams of FeS2. And we know the molar mass. We want to cancel out grams, and we want to get to moles. And it tells us that there's 119.99 grams per 1 mole. Once we have moles of our reactant, we just go to our chemical equation. Okay, and we can see that 4 moles of reactant makes 8 moles of product. So that's the next thing we're going to plug into our dimensional analysis. We want to cancel out moles of FeS2, and we want to get to moles of SO2. Okay, and from our equation we know there's 4 of these for every 8 of these. So once we plug that into our equation, we get 1.600 moles of SO2. Okay, the next thing we have to deal with is we have 55 liters of O2. 55 liters of O2 at 398 and 1.20 atmospheres. So what we know, 55 liters, 398 Kelvin, 1.20 atmospheres, and we want to know moles, right? We want to know moles so that we can plug it into our chemical formula, chemical equation. We use our ideal gas law. Our moles are equal to PV over RT. Our pressure, it's already in atmospheres, liters, and Kelvin. So we know our R values, so 1.20 atmospheres. Our volume is 55 liters. That's our oxygen. Our R is 0.08206. We'll leave those units off because they're long. And 398 Kelvin. We do that, and we get 2.02. And remember, this is moles of oxygen gas. We want to get from moles of reactant to moles of product. So we go to our equation. And we have 11 moles of oxygen for every 8 moles of product. We want to cancel out moles of O2 because they're up here, they're on the top, right? Everything over 1. We want to cancel out moles of O2, and we want to end up with moles of SO2. We do 11 over 8, and when we do that, we get 1.469 moles. Okay, so now we know that this is our limiting, because 1.46 is less than 1.60. But it's not asking for moles, right? It's asking for volume. So it's asking for the volume of SO2. So we found the moles of SO2. It's asking now for the volume of SO2 at standard temperature and pressure. So what we have to do here is solve, again, the ideal gas law. Volume equal to nRT over P. Right? Now it's up to us to know that STP is 273 Kelvin and 1 atmosphere. But from there we just plug in our 1.46 moles, 0.08206, and 273 Kelvin over 1 atmosphere, and we end up with our 32.9 liters, which is answer E. Okay, then the other one that a lot of people missed was number 4. So number 4, what's the density of oxygen gas at STP? The key there is you know the identity of the gas, so you have the molar mass in your pocket. So you know that oxygen, right, is one of our diatomics. Oxygen is O2, which means its molar mass is 32 grams per mole. And it's giving you STP. Whenever you have a gas at STP, you also have our 22.4 liters per mole, right, at STP. And that's one of our unit factors that's over on the board. Density is just knowing that it's grams per liter, and you have moles here, so you cancel out grams per mole times moles over liters. You end up with units of grams over liter, and 1.43 is our answer. So this is just a matter of knowing whenever you have know the identity of your gas, you know the molar mass. Whenever you have a gas at STP, you have your 22.4 liters per mole, and honestly, it's just committing that to memory, unfortunately. The next one that people were struggled with was number 6. Number 6 was just from the reading. So an instrument used to measure pressure of gas in a lab is called a manometer. That's that fun little instrument, the U-shaped one that has 2 different levels, right? You have your sample up top, you have the atmospheric pressure coming down, and this is usually filled with mercury. Right, so that's what a manometer is. And then number 9 was the next one that people struggled with. So this one, again, a lot of information, but this one was directly from the lab that we did, that mini lab. So number 9 was that collection of gas over water mini lab. We're generating hydrogen gas in a laboratory. We are given volume, we're given temperature, and we're given the total pressure. The giveaway here is total pressure, and they tell you they've given you a table of water vapor pressures. So we know we're dealing with the partial pressure of water, collection of hydrogen gas. It's an aqueous equation, so we're collecting this gas generally, probably, most likely over water, right? So kind of putting those together and doing it like we did in the lab problem. Okay, so the first thing we have to do is write down what we know. So we know volume is equal to 243 mils, which is equal to 0.243 liters. We know your temperature is equal to 25 degrees Celsius, which is equal to 298 Kelvin. We know P total, right? And it tells you right there in the question that it's total pressure. We know the total pressure is 745 millimeters of mercury, which is equal to 0.980 atmospheres. And we know the pressure of water at 25 degrees from that chart is equal to 23.78 millimeters of mercury, which is equal to 0.031 atmosphere. Okay, so we need, in order to solve this problem, looking for our hydrogen gas, we need the partial pressure of our hydrogen gas, right? And then we also need to know the moles of our hydrogen gas. So we've got lots of question marks, and then what we're ultimately looking for is the mass, right, of H2. But given this information, we know we're going to end up eventually solving for moles, and then from there we know the identity of the gas. So we know that H2, we always have that 2 grams per mole in our pocket. We always have our molar mass in our pocket just in case we need it. Okay, so first thing we can do is solve for the partial pressure of H2. So we know that P total is going to be equal to the partial pressure of water plus the partial pressure of hydrogen gas. Right, those are the only two things we're dealing with, so those are our two things in our equation. Our P total, 0.980 equal to 0.031 plus X. Our X, or our partial pressure of our gas, is going to be equal to 0.949 atmospheres, right? And we know it's in atmospheres, we already converted these. So our partial pressure of our gas is 0.949 atmospheres. So next thing we want to solve for is our moles of H2. So we do N, we have V, T, and partial pressure of water. So our partial moles of H2 equal to RT over PV over RT. PV over RT. And we know our partial pressure of our gas is 0.949. That's a 9. Our volume was given to us in the question. We need it in liters, 243 liters. We have liters, atmospheres, and Kelvin, which means we can use our 0.08206. Leave the units off because they're real big. And we're given our temperature is 298 Kelvin. We do that, we solve this for our moles of H2, and we get that we have 0.00943 moles of H2 being produced. But it's asking for mass, not moles. So we take our molar mass out of our pocket, cancel out moles, 2.00, we want to end up with grams, right? So whatever we have, whatever we want, so want over have, we want grams of H2, we have moles of H2, and we end up with 0.01885, okay, which is closest to our 0.0190. Right, we have to round to 3 significant figures. 1, 2, 3. That rounds up. That rounds up. 1.90. 0.0190. There we go. Alrighty. If you have any questions, I will be back tomorrow. Finish up your test corrections and hand them in at the end of class. And then don't forget you have the Mastering Chemistry assignment due for homework on Friday. Alright, Mastering Chemistry pre-lesson 6 and the post-lesson 5 is also due.